Okay, so whenever you think about surveying a population, what's the first thing that comes to mind? Probably simple random sampling, right? Everybody gets an equal shot. It's the gold standard, the definition of fairness. But here's a question. What if being fair isn't always the smartest way to do things? Today, we're diving into why statisticians sometimes decide to, well, rig the game a little. We're going to give some units a much higher chance of being picked, and you're going to see how this seemingly unfair approach can lead to results that are way, way more accurate.
So here's our roadmap for this deep dive. First up, we're going to expose the big flaw in equal probability sampling. Then we'll start building our alternative from the ground up, starting with the simplest case you can imagine, just sampling one single unit. After that, we'll put the two methods head-to-head to see who wins. We'll then scale it up to larger samples, introduce the really powerful concept of probability proportional to size, or PPS, and finally, we'll see how it all plays out in a huge real-world study.
All right, let's get right into it. To really understand why we need this new tool in our statistical toolkit, we have to start by seeing where our old, trusted friend, simple random sampling, can sometimes let us down.
You know, we're taught that simple random sampling is the epitome of fairness. But is it always the most efficient? I mean, does giving every single unit the exact same chance of being selected always give us the most precise estimate for our money? Well, the answer, and this might surprise you, is a resounding no. And let's look at a concrete example to see why.
So check out this study. The goal was to survey residents in nursing homes about their preferences for life-sustaining treatments. Now, the population consists of 294 different homes, but here's the kicker. They vary wildly in size. We're talking tiny homes and massive facilities. The researchers used a two-stage design. First, sample the nursing homes, which are clusters, and then sample residents within those homes. The most intuitive first step, and what they did, was to just take a simple random sample of the homes. And that, right there, is where the problem starts.
And this really gets to the core of the problem. When you do a simple random sample of the homes, a tiny 20-bed facility has the exact same probability of being chosen as a gigantic 1,000-bed facility. Just think about what that means. Let's say we then sample 10 residents from each home we pick. Well, for the small home, those 10 people represent half of its entire population. But for the large home, 10 people is just 1%. This creates what we call a non-self-weighted sample, meaning each person you interview no longer represents the same number of people in the total population. Not only does that force you to do a bunch of complex weighting later, but worse, it can lead to estimates with enormous variance. Why? Because the really big homes, the ones that contribute the most to the overall population totals, are just as likely to be completely missed as the tiny ones. So how do we fix this mess? Well, let's build the solution from scratch. Let's start with the simplest case possible. In this section, forget about sampling hundreds of units. We are going to sample just one, a single unit. But we're going to do it with these purposefully unequal probabilities, and this is going to give us a rock-solid foundation for everything that comes next. Okay, here's our first big idea. Our goal is to estimate the total for the whole population, which we'll call T. To do this, we're going to give each unit, I, its own special probability of being selected, which we'll call psi sub I, or psi. Now, if we happen to select unit I, our estimate for the total is simply its value, Ti, divided by its probability of selection, psi I. The intuition here is absolutely key. Think of it this way. If a unit has a tiny chance of being picked, but we get lucky and selected anyway, that one unit must be standing in for a lot of other similar units we didn't pick. So to account for that, we give it a huge weight by dividing its value by that tiny probability. Conversely, if a unit has a high probability of being picked, it doesn't represent as many unseen units, so it gets a smaller weight. It's a really elegant way to get an unbiased estimate. All right, let's make this super concrete with an example. We've got 4 supermarkets, and we want to estimate their total sales by sampling just one of them. Now, it's pretty reasonable to assume that sales are related to store size, right? So we're going to set the probability of picking each store to be proportional to its size in square meters. The total size is 1,600 square meters. Store A is 100, so its probability is 100 over 1,600, or 1/16. Meanwhile, store D is a beast at 1,000 square meters, giving it a much higher 10/16 chance. Now look at that last column. Let's say our one draw gives us store C. Its sales are 24, its probability was 3/16. So our estimate for the total sales of all 4 stores would be 24 divided by 3/16, which is 128. As you can see, our final estimate changes depending on which store we happen to draw. So we know our estimator is unbiased. On average, it's going to hit the right target, which is 300. But the big question is, How much does it jump around based on the luck of the draw? For that, we need to calculate its variance. The concept is pretty straightforward. For each of the 4 possible outcomes, we figure out how far off our estimate would be from the true total. That's our error, then we square that error, and then we weight it by the probability of picking that store in the first place. This formula is just the math that says exactly that. And when we plug in our numbers from the supermarket example and sum up those weighted squared errors, we get a final variance of 14,248. Okay, so we have a variance for our new method, 14,248. But honestly, a number like that is pretty meaningless by itself, right? We need some context. We need a benchmark. So in this section, we're going to stage a showdown. We're putting our new unequal probability method in a direct head-to-head competition with the old standard, simple random sampling. So let's rewind. What if we had just ignored the store size and used plain old simple random sampling? Well, in that case, each of the 4 stores would have an equal 1 in 4 chance of being picked, and the standard estimator for the total is the population size, n, which is 4, times the value of the unit we sampled. And just look at the wild range of possible estimates now. If we pick store A, we estimate a total of 44. But if we happen to draw the massive outlier store D, our estimate skyrockets all the way to 980. You can already just feel how much more unstable and unpredictable this estimator is going to be. And here it is. This slide just says it all. This is the moment of truth. The variance for our unequal probability estimator was about 14,000. The variance for the simple random sampling estimator? Over 154,000. I mean, that is just a staggering difference. Our new, smarter estimator is more than 10 times more precise. And this is the core lesson of this entire technique. If you have some extra information, any variable like size that's correlated with what you're trying to measure, you can and you absolutely should use it to design a more efficient sample.
Okay, that was a fantastic result for our simple little case where n equals 1. But let's be real, in the real world, we almost always sample more than 1 unit. So now we need to generalize what we've learned to a sample of any size n. To keep things a little simpler mathematically, we're going to start with the case of sampling with replacement. That just means after we pick a unit, we proverbially put it back in the hat so it has a chance to be selected again on subsequent draws. Let's have a look at our new estimator. So psi is still the same. It's the probability of selecting unit I on any single draw. We've added a new term, QT, which is just a simple count of how many times unit I actually showed up in our sample. Now the estimator for the total becomes an average. The best way to think about it is this. Each of our n draws is like its own little mini experiment, and each one gives us an independent, unbiased estimate of the total, just like in our n equals 1 case. So to get our final, more robust answer, we just run the experiment n times and average all the results. It's a really clean and elegant way to scale up our simple case. Now, for any good statistician, the first question you should always ask about a new estimator is it unbiased? Does it hit the right target on average? So let's quickly walk through this proof. We start with the expectation of our estimator. Now, thanks to a really nice property called the linearity of expectation, we can just push that E operator right inside the summation. The next bit we need is the expected value of Qi. Well, that's a classic binomial result. If you have n trials and the probability of success on any trial is psi I, then the expected number of successes is just n times psi I. We substitute that in, and then look at that. Everything just beautifully cancels out. The n's cancel, the psi i's cancel, and we're left with just the sum of the ti's, which by definition is the true population total, t. So yes, it's confirmed. Our estimator is perfectly unbiased. Okay, so that's great in theory, but in the real world, we never know the true variance. All we have is our one sample. So how do we estimate the variance from just that one sample? Well, the logic is very similar to how you'd calculate a standard sample variance. For each of the n draws in our sample, we look at the individual estimate it gave us and see how much it deviates from our final overall average estimate. We square those deviations, add them all up, and then scale them by the right factor. The formula you see here does exactly that, and it gives us a nice, unbiased estimate of the true variance using only the data from our sample. So far, we've been talking about setting these selection probabilities, the size, in a pretty general way. Now, let's zoom in on the single most common and arguably the most powerful way to actually set them in practice. This is a method known as probability proportional to size, or PPS sampling for short. The whole idea behind PPS is incredibly intuitive.
In so many situations, the total we're trying to measure, like total sales or number of physicians or number of defects, is related to some measure of size, like square footage or county population or the number of employees. PPS formalizes this intuition. We define the size of each unit as MI, and the total size of all units in the population as M0. Then we set our selection probability, psi-I, to simply be that unit size divided by the total size. It does exactly what it says on the box. Big units get a bigger chance of being selected. And this is where it gets really cool. Here's the beautiful result. When we specifically use PPS sampling to set our probabilities, our estimator for the population mean, it collapses into something wonderfully simple. It's just the plain old average of the means from the units in our sample. All that complex weighting we did up front, it perfectly cancels out in the end, leaving us with a final calculation that is powerful, elegant, and really, really easy to compute. We've covered a whole lot of theory. It's been fun, but now it's time to see how this all comes together in a large-scale, real-world application. Let's take a look at how PPS sampling was actually used to estimate the total number of physicians across the entire United States. So in this study, the primary sampling units were U.S. counties, and they were sampled with probabilities proportional to their population size. Now, take a close look at this sample data. Do you see Maricopa County, Arizona listed twice? That is not a typo, because we're sampling with replacement and Maricopa is a massive county with a very high selection probability. It's totally possible and even expected for it to be chosen more than once. Each time it appears, it just counts as another independent observation in our sample of 100. So after all that, what did they find? Well, from their sample of just 100 counties, they estimated the total number of physicians in the U.S. was about 570,000, with a standard error of around 41,000. Now, the actual true value from a data book was about 532,000. Look how close our estimate is! The true value is well within one standard error, and it falls squarely inside our 95% confidence interval. This is a fantastic real-world validation of the method. It just shows the incredible efficiency of this approach. With a tiny fraction of the total counties, we got a really accurate picture of the entire country. So we've seen just how incredibly effective PPS sampling can be, but only when your size measure is strongly correlated with your variable of interest. But remember, no statistical method is a silver bullet. And that leads us to one final critical question. When would this powerful technique be the absolute wrong tool for the job? What if your size measure is completely unrelated to what you're measuring? Or even worse, what if it's negatively correlated? Because thinking about the limits of a tool is just as important as knowing its strengths. And that really is what separates a good statistician from a great one. Thanks for joining me.